So, we are discussing about the hydride generation atomic absorption. What I have told you is that it is a simple modular attachment. We take the chemistry to atomic absorption, convert the metals into hydride, take it into the flame and do the analysis. So, in the flame most of the hydrides have got a property to decompose, produce metal atoms. Once these metal atoms are produced, all other mechanisms remain the same, because they absorb the radiation, go to next higher energy level. During that process they need absorption, and that absorption comes from the hollow cathode lamp. So, we have discussed this, and this is the hydride generation system. It is a closed system with sample acidified sample solution. I add sodium borohydride, and this is the norm nowadays instead of zinc and hydrochloric acid. And then the sample is transferred to the heated quartz tube here, and then there it gets decomposed and the chemical analysis gets completed, because we measure the transmittance. Okay. So, I have given you the reaction of the zinc hydrochloride as well as sodium borohydride. In both cases there is nascent hydrogen generated. So, this nascent hydrogen will react with selenium, tellurium, bismuth, arsenic, antimony, lead, mercury, etc., all those germanium also. So, these 6 elements form hydrides, just like SiH2, selenium hydride, tellurium hydride, bismuth hydride, lead hydride, etc. And once into the flame it gets decomposed, giving you selenium and hydrogen. So, this selenium will undergo a oxidation reduction process and then forming the free atoms, and the free atoms are measured in the absorbance. So, I have also told you that the most important part of it is you can use about 0.5 ml of the sample, and you can dilute the sample 0.5 ml. Suppose you dilute it 1000 times, then what happens? Because it is an absolute technique, the detection limit will reach parts per million or parts per billion level. Even parts per trillion level instruments are nowadays available, which makes it one of the most powerful technique for the determination of arsenic, antimony, selenium, etc. And these elements are the most toxic elements we have ever known. And the requirement of chemical analysis is that sometimes we want to determine arsenic in the blood, and then selenium in the bovine this thing, sometimes selenium in the brain, and all these things. I think most of you have heard that Napoleon Bonaparte was poisoned with arsenic. Even now we are trying to determine how much of arsenic is there in his hair. So, it does not go away. So, these absolute detection limits of 0.5 ppt are possible using hydride generation technique. That is why I am teaching you this thing, and the beauty is you can have a throughput of 30 samples per hour. That means you can have any number of samples and then keep on doing the analysis very fast. We are discussing about the interference, the mechanism we have discussed. It is the generation of hydride radical, and this recombination reaction of selenium and hydride, even though it is minus 3.5 kilocalories thermodynamically, it does not go through because it requires a third party according to chemical thermokinetics principles. Okay. We have discussed interferences. The interferences mostly arise from kinetic problems, that is carrying out the reaction and taking it into the flame. Okay. So, it is possible for us to estimate whether an element is in plus 5 state or plus 3 state, because plus 5 state, suppose I have I take one sample, oxidize everything to plus 5 state, I have all the reaction, and then reduce it, then we have plus 3 state. What is the difference between the two? That gives me speciation, whether arsenic is plus 5, arsenic is plus 3. So, plus 5 is more dangerous than plus 3. Like that, chemical speciation is something very important that has been achieved using this arsenic hydride generation, but for group 6 elements it is not +5 and +3, but it is +4 and +6. So, that gives a measurable signal. We had discussed up to this level, this is only for your benefit, again reproduction, and then in practice a pre-reduction of selenium and tellurium is always required in hot 4 molar or 6 molar HCl. These kind of details nobody will teach you in the class or anywhere else. This you have to learn it from experience, but from my experience I am trying to give you the typical method how you should intuitively go for the chemical analysis, because especially selenium and tellurium are the most toxic elements we have ever known. Many health episodes and other things, toxic spills and other things have happened because of this selenium, and selenium is one of the known contaminant along with lead also. So, it is normally if I have lot of acid HCl, H2SO4, HNO3 etc., they depress the signal if present in high concentrations. So, we have to be very careful that the concentration of the acid should be as low as possible in the whenever we want to do this atomic absorption using hydride generation. So, what is the effect of nitric acid? Or you can see here I have plotted relative sensitivity, that is approximately 1 ppb, 1 part per billion chemical analysis of arsenic, selenium etc. What we have done is we have increased the acidity from 0.1, 0.2, 0.3, 0.5, 1, 2, 3 and 10 normal, 10%, not normal, percent. So, if I have 0.1% of the nitric acid, this nitric acid, the signal is somewhere here almost 100%. That means acid does not have much effect on the signal. Now, suppose I increase it to 0.3, where do I end up? I end up with about 92 to 93%. Increase the acid still further, 0.5%, I have about 80%. Increase it still further around 1 normal, we have about 70%. I increase it further for tin to about 4, 5 normal, you can see that signal is hardly less than 10%. So, this shows you the effect of acid in the sample. So, whenever you collect a sample for arsenic analysis, what you should be doing is you must find out what is the acidity in that. You may perform a small titration and find out what is the acid, then you try to decrease the acidity to fit back into 0.1 normal or 0.2 normal, where the signal will not be affected. Same thing is true with selenium. You can see with selenium it is slightly more acid tolerant, because up to 1.5%, you can see that I have drawn a log scale here in percent HNO3, whereas this is a relative sensitivity, it is a transmittance. So, with selenium up to almost up to 1%, I do not have a problem, but the moment the acid percentage increases in the sample, it is decreasing to about 80%, no, around 90% between 2.5% acid. Increase the acid, again there will be problem, and same thing is, so this is all part of my own research which I have conducted earlier on atomic absorption. So, this data is fresh from my stock rather than from a textbook. Same thing is true, similarly we have done all this antimony, above 2%. In general you can say that above 2% there should not be more acid, but suppose more acid is there, then what happens? The hydride generation will be more. So, the formation of this hydride, metal hydride is more, but the signal will depress. So, it is a compromise, you have to organize between these elements for arsenic, arsenic you can see here, it is absolutely no problem up to 10% acid also. That is one of these. Why we do this acid, effect of acid? Because we take the sample, dissolve it in acid. 99% of the chemical analysis we do dissolve it in acid. That is why we should be worried about the acid content in the hydride generation AAS. Similarly, quite often we use sulfuric acid also for dissolution. This is the effect in sulfuric acid. For example, look at tin, where it comes. By about 1% tin is gone. Sample analysis signal is approximately only 20%. Antimony is slightly more tolerant, like that you can study all these reactions, arsimony, etc. Then we have the other interferences in hydride generation. You see, I have already told you so many times that atomic absorption is basically an interference free analysis, but so long as only the metal atoms are there, it is interference free. But interference can come from flame, it can come from precipitate, it can come from so many other spectral interferences are there, vapor phase interferences are there, transport interferences. All these things do contribute some amount of interference in the determination of almost all elements. So, what happens? I have tried to gather some amount of information regarding the hydride generation interferences. So, sometimes precipitates form, for example, nickel, platinum, etc. They absorb hydrogen, they are all very well known hydrogen absorbers, even used even in petrochemical reactions. And we cannot have platinum as an in the sample. The moment we have platinum, you do not have hydride generation at all, because it absorbs all the hydrogen, and you will be wondering what happened to the hydrogen generation reaction. Sometimes transition elements interfere in the ionic forms. So, EDTA, cyanides and thiocyanates, these things mask the interference. So, these are the techniques people use whenever there is certain amount of interference in the sample. So, all hydride forming elements basically they interfere naturally. So, mutually also. So, if you are determining arsenic, there is some amount of selenium, again there may be some amount of interference. So, but not much, because it is element specific. Whatever is the frequency coming from only hollow cathode lamp, if it matches the other elements, then there will be interference, otherwise not much. That is what makes the hydride generation atomic absorption a very beautiful technique, capable of determination of parts per billion, parts per trillion quantitatively. It is not, it is like finding needles in a haystack, but not just one or two, the total needles in the haystack. So, interference is dependent upon the absolute concentration, but not on the analyte or interference ratio. So, arsenic selenium interference is a gas phase interference, that we cannot do much. We just have to use a technique, that is using a buffer. What we do is we use a buffer to delay the arsenic evolution. Then you do the selenium and then you do the arsenic, then you can determine both of them in the same sample. And then now I want to show you what is the basic technique. Here I have the monochromator, this green color, and radiation comes through this, and here I have put a detector on the back side actually, and then this is my T tube through which the sample will come, and this is the volatile hydride generator. Volatile hydride generator is here. I have a standard blank, standard 1, and then standard 2, standard 3 unknown. It is basically a manifold. I can choose any sample I want to introduce into the flame, this T tube. So, the basic procedure basically remains the same. You introduce the blank, generate hydride, take it through this manifold into this. blank will be 0. Then you introduce your standard one and then again take it through the same thing, manifold, standard 2, standard 3, measure your unknown, and then it is as simple as that. Basically it is a relative technique, any atomic absorption. There is a technique where you can do absolute analysis, but that will come in graphite furnace, that I will teach you a bit later. Okay. Now, here is the proof that how much sample can be determined using hydride technique. Arsenic is there 0.02 ppb parts per billion, and bismuth 0.02, antimony is 0.1, selenium is 0.02, and tin is 0.5, tellurium is 0.02. I can increase the sample volume, increase the detection limit also, because it becomes an absolute technique, because it is taken out of the system. Whatever is the concentration in the sample, it does not make a difference, because only the arsenic hydride will come out. So, interference from other system also will be very less. So, this serves you, but you have to remember that we can determine only hydride forming elements, because most of the elements which form hydrides decompose into metal and hydrogen. They do not decompose into ions. Okay. So, this gives rise to a beautiful automation technique, whereas where the high sensitivity and the environmental pollution potential of arsenic, selenium, lead, etc., people have been working on this to automate the sample. There is a river, all the time river is flowing, somebody is polluting all the time, you need to determine the pollutant all the time, maybe 10 samples, 20 samples, 100 samples. Today Ganga is polluted and tomorrow also it is polluted. So, you want to know how much of arsenic is there, how much of selenium is there, everybody is somewhere something will be coming on. So, automation becomes a very important technique whenever you have to do a repetitive analysis. So, this kind of work requires peristaltic pumps. So, you just put the sample, it will keep on generating, adding, and then taking it into the sample detector and sample holder, automatically results will come that can be analyzed and evaluated even statistically also. So, we need pumps for mixing the reagents, and then we need nitrogen for hydride transport. Sometimes what happens, the moment we add mixing reagents, we need to take it into the flame. So, I have to pass nitrogen, because nitrogen will fill the liquid and push out the hydride gas mechanically, it is a mechanical process. So, there is a time lag between the addition of the sample and by the time it is taken to the sample. So, this time lag can be automated. Say I add the sample now, after 1 minute later this pump nitrogen gas will switch on and push all the sample. So, it gives me also a way of controlling the whole reaction for a number of sample analysis, that is the beauty. So, these operations can be integrated into the software of atomic absorption, and throughput of 30 samples per hour is possible, and there we end our discussion with respect to hydride generation, atomic absorption. If you need more information, I would refer you to some of the books which I have already given in the beginning of the course for more information. Of course, there are many journals dedicated to atomic absorption, spectrometry, which can be consulted for more recent applications. Most of the applications of atomic absorption nowadays, they refer to sample treatment and increasing the sample specificity. That means whatever is the interference, that has to be minimized, make the analysis very specific. So, another technique which I want to introduce to you is Mercury cold vapor technique. This beautiful technique you must understand because it is not necessarily a part of atomic absorption which I am teaching you as a course, but it can be a part of atomic absorption as a modular attachment, just like this hydride generation AAS. So, what happens here? Mercury is the only metallic element that exists in the atomic state at ambient temperature. You spill certain amount of mercury here, it will be there in the air, and mercury is very toxic. It is very well known because mercury since 1955, ever since that Minamata Bay disease in Japan, where mercury containing effluents used to enter the sea, they used to, fish used to absorb them through the gills, and then people used to eat the fish, because I think Japanese must be very happy to eat fish. They all like it, just like our Bengali brothers. And the problem was mercury created lot of health problems with them. So, the factory making benzaldehyde used to let out mercury because they used to use mercury as a catalyst. But this disease was identified as Minamata Bay disease because it occurred in Minamata. Still earlier, during medieval times, people used to wear big hats in Europe. The hats used to contain feathers. These feathers, people, the hat makers used to fix it with mercury paste. They used to get affected, and they used to, mercury has got a neurological effect on the brain. So, they used to call it mad hatter's disease. Over a period of time, some of the hat makers used to go mad. So, it used to be called mad hatter's disease. So, but the world concentration on mercury toxicity happened because of Minamata Bay disease, because earlier at that time during medieval times, then people might not have bothered about the toxicity, where it came from, etc. Because many of the alchemists used to work in very high polluted atmospheres. Even Marie Curie used to work in radioactive laboratories where pitch blende, etc., where she died of cancer. So, that time awareness was not much. So, coming back to this atomic absorption mercury, it has a vapor pressure of about 0.0016 millibar at 20 degrees, which corresponds to 14 milligram per cubic meter. So, that means nowadays the standard is about 0.001 milligram per cubic meter, that is the standard we are supposed to breathe. But normal spilling in the laboratory gives you 14 milligrams. So, given the environmental pollution potential, attempts have been made since 1939, well before the development of AAS, for the determination of mercury. In fact, the determination of mercury was achieved up to 0.13 ppm in 1913 itself by the same vapor technique. So, the most successful among these was electrolytic deposition of mercury using a mercury vaporization cell. What we do is take out mercury from a given sample, put it on a metal. We know that mercury forms number of amalgams with any metal. What they did was they take out from a given sample, release mercury as a element, and then the mercury vapor will be carried out into the into a tube on which it will be connected, on which it will be contacting a metal piece. So, mercury amalgam will form. So, the beauty of mercury amalgam is to decompose mercury. Any amalgam you heat, it will release mercury. So, the technique of analysis, what happens is you take the mercury, put it on a metal, heat it, release the mercury, take it to atomic absorption, because you already have mercury in the gaseous phase. Mercury atoms are already there. So, the determination of mercury was one of the most successful quite early days of atomic absorption. So, Politkovs and Wittgen were the first to use the stannous chloride to reduce mercury in sample solutions, which resulted in unusually large absorbance signal for mercury in AAS. Subsequently, they eliminated the flame and nebulizer, both of them they eliminated and passed only air to conduct the vapor through a 30 centimeter quartz cell mounted in the optical path of the radiation beam. That means, instead of the flame, they put a 30 centimeter quartz cell in which the mercury was carried in. So, with this technique they obtained a detection limit of 0.5 nanogram per mercury. So, a general scheme of generation of mercury vapor is shown here. What we have here? We have a sample flask containing the sample, I have a bubbler here, and then I have a pump, and then this is the three-way wall, and then absorbent, and then sample comes here, I just bubble the sample and then take out the mercury vapor through the drying tube into the atomic absorption cell and measure the absorbance like this, and this goes out, mercury goes out, and then the requirement is sometimes we need the drying agent, very important aspect of determining mercury. So, nowadays the determination of mercury is carried out by an apparatus similar to that of hydride generator, but provided with some modifications, because stannous chloride is used as a reductant. So, air must be pumped through the solution to agitate as well as transport the mercury to the absorption cell. The dynamic signal generated in this way shows a slightly lower absorbance compared to sodium borohydride generation acid solution. So, you can use sodium borohydride acid or stannous chloride and HCl, both have got the capability to reduce mercury ions into atoms. So, with sodium borohydride, a great quantity of hydrogen is liberated when acid is added. This hydrogen in fact transports the majority of the metallic mercury into the absorption cell. So, it is helpful. Further, the reaction with sodium borohydride is much faster, so that the peak height is measured with the open system, and it is almost equal to that of stannous chloride in a closed system. That means, you can use peak height for measurement whether you use sodium borohydride or stannous chloride. Only difference is with sodium borohydride, it is a much faster reaction than the stannous chloride. Now, mercury cold vapor signal is like this. Sometimes you have to make a automated signal, and with sodium borohydride you can see the sample analysis here. The reaction is so fast, and every time you have a sample, the signal is same sample I am injecting. So, this peak is very uniform. Okay. So, the peak area also seems to be quite uniform. This is first peak, second peak, third peak, fourth peak, etc. And all of them seem to be uniform. That means, consistency of mercury determination is very good in sodium borohydride. whereas with stannous chloride you can see the peak is like this. Okay. I give a gap, take one more signal, comes out like this. So, in this case peak area, measurement of peak area makes more sense than peak height like this. Okay. So, quite often the reproducibility is very important with respect to peak height. So, by using a well designed reaction vessel which I had shown you earlier with a conical bottom and introducing the reductant near the bottom of the vessel and thorough and turbulent mixing of the reductant, all these things ensure complete displacement and carryover of the mercury. The time required for the reaction is only 1 or 2 minutes. This is also very important in atomic absorption measurement or method. The time saving is most important. The whole measurement should be over within a few minutes, maximum 1 or 2 minutes, maybe a few seconds, maybe 30 seconds, 40 seconds. That means whenever you are doing integration, you have to do it for longer time, because the signal will not come to baseline. So, the with sodium borohydride reduction has assumed more importance with respect to this stannous chloride reduction. Since mercury vapor is in contact only with the tubes and other components of the apparatus only for a very short time, the exchange reactions play only a minor role. That means the exchange of the metals, adsorption of on the pipes, tubes, etc., it is not much, because it is in contact with the tubes and other things for very short time. So, in contrast, on a closed system, losses occur through absorption and carryover problems also from one to the next or more. What do we mean by carryover problems? The carryover problem means the signal is not totally free from the blank or from the previous sample. See, basically whenever we do chemical analysis, first we introduce the blank and then we introduced one first standard, then second standard, third standard, etc. Then put the sample, take the absorbance and refer it. So, whenever we are doing an integration, what we want to do is during integration we give a time gap that is at our disposal. Suppose I give 1 minute, the sample has not yet come out totally, some small portion is remaining, that will get carried over to next sample. That means the absorbance reading what you get would be different than what it should be. So, first one will be less, second one will be more, third one will be much more, like that the whole calibration curve can get biased. This should not happen. So, an enhanced signal is normally obtained and that is carryover. The necessity of determining mercury in ultra trace quantities has led to the development of enrichment and separation techniques. The fact that mercury forms stable amalgam with noble metals such as copper, silver, gold can be used to advantage for enrichment. What I can do is, suppose mercury is in parts per trillion level. Okay. So, the first I take a small sample, add the sodium borohydride, take the mercury, put it take it to an electrical take it to a gold foil and adsorb the form the amalgam, and that is that. Then I can take another sample, carry it to the same metal, and then mercury gets adsorbed on that, because mercury amalgam does not have a specific composition. So, it can keep on concentrating. So, I take 5 ml put it on the gold plate, small 1 centimeter or 0.5 square centimeter gold foil will do. On that I can take 100 samples and concentrate. That means then I can divide the total result by about 100. If I can do it by 50, I can divide it by 50. That means for each determination the actual concentration can be increased, there is no limit theoretically, but I can do it 3 times, 4 times, etc. That should not be a problem at all. So, the mercury vapor is merely collected by amalgamation on gold gauze, that is for sufficiently long time to concentrate it. Subsequently, the gauze is heated to 500 to 700 degrees and the vapor is carried over to the absorption cell for measurement. Once you heat the electrical piece, that gold piece, all the mercury will get released and gold will become fresh, ready for another analysis, and mercury is transported to the atomic absorption system. The beauty is you do not need a flame in atomic absorption. The mercury vapor, cold vapor generates the mercury in the vapor phase, mercury atoms only in the ground state, that is the bottom line. So, an enhanced signal can be obtained for multiple analysis for direct measurement. So, this is what happens with amalgamation. What I am doing here is I am with 250 nanogram mercury, if I do analysis directly, that is with tin etc., you can see here the signal will keep on going down. Okay, this is the analysis volume. This is the effect of volume. If the sample is about 10 ml, I have absorbance of about 0.25, and the same sample, if I increase the volume to 25 ml, then it is approximately 0.2. Like that, there will be a problem with this, but with amalgamation, you see my signal, whatever is the analysis volume, it does not matter 10, 20, 30, 40, but my absorbance is 0.32, 0.32, 0.32 for 25 ml, and then same 0.32 even for 50 ml. So, that is the beauty of amalgamation. Okay. Since the amalgam technique pre-concentrates the mercury, the method becomes independent of the volume of the sample and absolute determination is possible. In this way, detection limit of the cold vapor mercury is also improved. So, we will continue our discussion on the interferences slightly in the next class, and then we will move on to flame emission spectrometry. So, thank you very much.